Good morning. My name is Rayna, and I will be talking about the history, importance, and endocrine and reproductive impacts of PFAS on wildlife. I'm sorry, my voice is pretty gone. I've been sick for a bit now. In this presentation, I'll be going over what is PFAS, what are some of the common uses of PFASs, the difference between long and short chain PFAS molecules, some of the regulations that have been put towards these chemicals, the endocrine and reproductive effects these chemicals have on fish and other wildlife, and finally, the conclusion. So to begin, what is PFAS? So PFAS stands for per- and polyfluoroalkyl substances, which are man-made molecules belonging to the chemical class of organofluorine molecules. Organofluorine molecules are known for their great chemical and thermal stability, along with their resistance to heat, water, and oil. The great stability of these molecules can be attributed to the carbon-fluorine bond, which has one of the strongest bond energies in nature. But since these are man-made, all of the biologically produced fluorinated organics have only one fluorine atom, while the man-made counterparts have many fluorine substituents or maybe fully fluorinated, which further contributes to their strong stability. So over here we have a PFAS molecule, and you can see the carbon-fluorine bonds and how this is one of the man-made ones and how it has these multiple fluorine atoms, which make it extremely stable. There are almost 5,000 different types of PFAS molecules that have been produced for over 50 years. And due to their desired resistance and stability properties, they are found in a large array of different products, and they can be found in many regular items such as paper, nonstick cookware, some food packaging, leather and textile coatings for stain repelling purposes, pesticides, paints, and firefighting foams. So PFAS in the environment. PFAS have been detected in all mediums, such as water, air, sediments, and organisms, and in 98% of the blood of humans in the United States based off a study. So studies have found that the major sources of PFAS into the environment are manufacturing facilities, the discharge of firefighting foams, treated wastewater, runoff, and landfill leaches. Unfortunately, the same repellent and stability properties that make PFAS so desirable for use in many products also make them potentially hazardous to organisms in the environment, which make these chemicals highly persistent and bioaccumulative, and having toxic potential. So PFAS chemicals have been found to bind to blood and accumulate in the liver, which contributes to their potential for bioaccumulation. And some of the known effects of PFAS include their effects on lipid metabolism and reproduction, and they impede on cell-to-cell communication and peroxisome proliferation, both which are activities that can lead to carcinogenesis in liver, which is not good. And some exposures of different PFAS chemicals can lead to an increased risk of developmental effects on fetus and infants. So, as previously mentioned, there are over 500 PFAS molecules that have been commercially active in the last decade, but some of them have risen to the top of scientific agendas due to their concern. And these are the perfluorooctyl molecules, or the long-chain PFAS molecules, which have been highly studied, and they include the PFAS chemicals of PFOS and PFOA. These long-chain molecules have been found to be highly bioaccumulative and cause a lot of adverse human and environmental health effects. So in the last decade, there's been an urge to phase out these long-chain PFAS compounds and switch to short-chain molecule substitutes that are thought to have fewer toxic effects and be less bioaccumulative due to their increased solubility, fast elimination, and reduced affinity for binding targets. And this main short-chain substitute that has been manufactured and used is PFBS. So down here, I have like a brief little timeline of some of the regulations and efforts that have been put out there to control or lessen the impacts of these PFAS chemicals. So in the 1950s was the creation of PFAS compounds. And then in 2002, after technology and studies increased on these PFAS molecules, 3M, the principal producer of PFAS worldwide and the only producer of PFOS in the United States, phased out PFOS and switched to alternative PFAS chemicals after a lot of pressure was put on them to do so due to the known effects of PFOS. And then in 2008, the EPA's PFOA stewardship program successfully phased out many long-chain PFASs in 8 participating companies that were participating in this program in favor of switching to the shorter chain replacements. And then later, the EPA issued significant new rules to restrict the future use and production of 183 PFAS chemicals. However, this new rules still allowed for continued low volume use of some of the restricted PFAS compounds in certain industries, and it allowed for the use of already produced items like firefighting foams. So that was somewhat of a success, but also not completely because it's still allowed for use. And then in 2009, Annex B of the Stockholm Convention was amended to include PFOS as a persistent organic pollutant. So with the new regulations in place to phase out harmful long-chain PFAS and switch to new and improved, apparently short-chain molecules, it may seem like the worries about PFAS in the environment are kind of over, and it's kind of like a issue of DDT, which it's not being released anymore, and we're just kind of dealing with the effects of past production. But however, that's not the case. And this switch to the shorter PFAS chemicals still has some complications, and that complications as a result of lingering contamination from legacy PFAS chemicals that are still remaining and persistent in the environment. And also there is a huge lack of knowledge and uncertainty on the effects of these newer short chain molecules like PFBS that are now being highly produced because they're thought to be so much better than these old ones. And also some of the known degradation products of these short chain compounds are to long chain PFAS, so it may still be putting these long chains out there. So clearly the restrictions on these long chain and phase out of them have not solved all the PFAS problems, and it's important to study the range of potential effects that these chemicals have on wildlife. And here is just the structure of PFBS, and you can see that it's a shorter chain molecule than PFOS, excuse me, and PFOA. So now we'll switch and look into some case studies and evaluate and compare the reproductive and endocrine effects on wildlife between the long chain and short chain molecules to evaluate if these short chain molecules have really alleviated any continued cause for concern about PFAS chemicals in the environment and their effects on wildlife. So we'll begin by looking at the endocrine and reproductive effects of these chemicals in fish. So here we can see that many studies have been conducted in order to understand the effects that PFAS have on fish endocrine systems and reproduction. And unfortunately, varying test species, different exposure times and concentrations have led to a widespread scale of effects that have been caused by these long-chain PFOS and PFOA in fish. So now we'll just take a look right here. And we can see that a study done on the effects of PFOS in fathead minnow found no effects on fertility or the gonads of adult males, no significant changes in vitellogenin levels, but it did, however, reduce fecundity and spawning and delayed maturation and release of ova in these fathead minnow. A study done on PFOS and PFOA in freshwater male tilapia saw induced vitellogenin production after exposure, and that when in organisms exposed to both PFOS and PFOA in addition to E2, which is highly found in ecosystems due to the large spread use in the United States of this estrogen in birth control and other different hormonal uses, anti-estrogenic effects were seen. So that is important to look at the paired effects of these two chemicals and see these results. Another study on the effects of PFOS on zebrafish saw there was no change in sex ratios or effect on testicular morphology. It did find that exposure inhibited growth of gonads in female fish, and that vitellogenin gene expression was upregulated in both male and female fish. It also saw that F1 generation embryos and larvae, which were derived from maternal exposure, suffered from malformation and mortality, which is, again, another important finding. A study on the effects of PFOS on swordtails, again, saw no significant effect on sex ratios or fecundity, and no change in the gonads, in the weight of the gonads in male fish. It did see vitellogenin expression was first downregulated, then upregulated later in the study. And it saw that F1 generation survival rates were significantly lowered as compared to the control in offspring of exposed groups. And then a final study in PFOA in Japanese rice fish saw suppressed fecundity over 3 generations, which is a big finding, and accelerated gonad development in these fish. So again, a pretty broad, widespread set of findings on these effects of these long-chained molecules on fish. So then we'll switch over to a study by Chen et al. On the effects of PFBS on marine Medaka on the reproductive system. And so basically the study looked at environmental realistic concentrations, and they found that life cycle exposure of PFBS skewed sex ratios toward male dominance, and that's what this graph is showing over here. You can see the exposure concentrations on the x-axis, and as the exposure concentrations go up, you can see the y-axis, the male to female sex ratio in the first generation is showing a pretty significant skewing of the sex ratio towards male dominance. The study also found that exposure compromised female reproductive functions like shrinking the ovaries, blocking oogenesis, and lowering fecundity. Exposure also disrupted the reproductive endocrine system with anti-estrogenic activity found in female fish and estrogenic activity found in male fish. So that is not ideal. And these results also indicated that the adverse effects on the F0 generation were transmitted to F1 and F2 offspring, which is important for showing how significant exposure on one generation can be passed to following generations, which is important in showing that maybe PFBS is not as safe as it was originally thought to be. So then another study done on PFBS exposure, again on marine Medaka, and by the same authors, but a different year. They just love to look at PFBS exposure in marine Medaka. So they were looking at thyroid hormones, and since thyroid hormones are strongly connected to the development of visual systems in vertebrates, they wanted to see how life cycle exposure to PFBS would affect this. And they exposed marine Medaka embryos to PFBS concentrations, and their results showed that PFBS accumulated in eyes and induced ocular toxicity, and it also decreased the weight of eyes, but increased the water content in the eyes of female Medaka. It disrupted neural signaling processes and adversely affected the expression of eye proteins that are related to visual function and motor activity. So some important pathways were disrupted by this exposure. These findings are pretty significant because it shows like another endocrine system that is affected by the effects of PFBS. And it's also important because defects in visual systems can compromise an individual's ability to carry out different life activities like defense and different feeding behaviors, which can all contribute to its ability to survive and lead to a decreased survival in the wild. So it's kind of showing these more acute effects that are direct mortality caused by PFBS, but more so mortality caused as a result of a weakening functioning system, which is a result of PFBS on these systems. So now we will be looking at the effects that PFAS compounds have been found to have on other organisms that are not fish. So this first study looked at the exposure of PFBS on maternal mice, and it found a lot of detrimental effects on the offspring, and they saw decreased prenatal weight, delayed eye opening, and other delays in the reproductive development and development of these offspring. They also found there to be permanent hypothyroxemia in maternal mice, which is basically a permanent downregulation of a hormone that the thyroid produces as a result of PFBS exposure. So that's some effects in mammals. A study done on PFOS and PFBS exposure on C. elegans, which looked at, they compared similar internal concentrations of PFBS and PFOS, not similar exposure concentrations, which the majority of studies do. In this study, they found that as similar internal concentrations in organisms, PFOS and PFBS express similar toxicities. And they found that both chemicals reduced fecundity and downregulated vitellogenin production, which again is not good. And a final study looked at the effects of PFBS on quail, and it found no reproductive effects on exposed birds as compared to control. So again, a lot of variation. So in conclusion, there's a lot of variation in the literature on the exact effects of PFOS and PFBS on different organisms, but it is clear that high concentrations of these chemicals have detrimental effects on organisms. The results overall show that PFOS exhibits a higher reproductive and endocrine toxicity at lower concentrations as compared to PFBS due to its ability to bioaccumulate, while PFBS has still been found to not bioaccumulate in systems. But however, PFBS exposure has still been shown to skew sex ratios, accumulate in the eyes and affect visual development, and affect fecundity and vitellogenin production in varying organisms. So these documented effects combined with other studies showing no effects of PFBS on reproduction and endocrine activity would suggest that further research is necessary, especially when the production and release of PFBS into the environment is only growing, and higher PFBS concentrations will be exhibited in these ecosystems, and they'll be contributing to effects that are not fully understood. So it's important that further research is done so that we can further understand these effects in order to understand the effects. So some ideas for further research on PFBS and PFOS would include looking at the exact paths of endocrine disruption so that we can see how these chemicals are fully going about their disruption, which isn't completely known thus far. Looking at doing more long-term studies. So just like full ecosystem studies of what PFBS and PFOS in ecosystems at a constant rate being inputted does to these studies on like year-long scales. And also looking at the effects of PFBS combined with other chemicals. So kind of looking at PFBS with E2 or EE2 and other hormones that are found, other endocrine disrupting chemicals that are highly found in environments, and how those affect, just because that's how these chemicals are being found in organisms. They're not just alone, they're with a slurry of other chemicals that are having effects on these wildlife. So I also think that increased wastewater treatment strategies, as well as tighter regulations on the use of PFBS are necessary until the effects of these chemicals on ecosystems is fully understood. So I don't think that just having no regulations on PFBS until we start seeing detrimental effects is a good idea. I think that regulations need to be put in place to kind of control the amount of PFBS that is being inputted into these ecosystems by companies, so that we don't catch the air too late like we tend to do in chemical studies of pollutants. But yeah, that is my presentation on the effects of PFAS and their importance in history. We're excited for all the information that was used in this presentation. And that is it. Thank you for listening.